7. Because you take this whole expression, you plug it into your function, and find what value of alpha is going to give you the minimum. So this is what's called a line search. Okay. So from this point, you know you're stepping in this direction to your new point, you just don't know how far to step. You want to make the most progress. So you choose alpha's optimal in the sense that it basically gives you as much progress as you can get. Then you're at x1, y1, and you repeat the process with a new steepest ascent direction. So if the value of the function keeps getting smaller and smaller, and you keep doing this until you get to a minimum. So that's one application of steepest ascent. Now that is a rudimentary procedure which doesn't necessarily work well, but this idea of using the steepest ascent direction is very useful in the whole field of optimization, which is all about finding minimum values of functions, and we'll spend some time on that next lecture and the one after that. Okay. Involving directional derivatives. So f of xy be equal to x squared y plus y cubed, and we're interested in what's happening at a particular point. That's 2 and minus 2. So we go ahead and compute the gradient. So it's going to be 2xy for df dx, and then the derivative with respect to y is going to be x squared plus 3y squared. What that means is if we evaluate this at this point, 2 and minus 2, the vector we get is minus 8 and 16. All right. So now, if you look at the directions of steepest ascent and descent, so the direction would be the gradient at this point divided by its length. So it amounts to normalizing this vector. Now the magnitude of a gradient at this point, that's going to be square root of 8 squared plus square root of 16 squared. So that's the square root of 320. So that's 8 times the square root of 5. Right. So by normalizing this vector, our direction of steepest ascent is going to be minus 1 over square root of 5, 2 over square root of 5. All right, so that's going to be this direction. So steepest ascent. Whereas for descent, we just negate this. So that's 1 over square root of 5 minus 2 square root of 5. So just going the other direction. Okay. And finally, no change, directions on which the function doesn't change at all. We need a vector that's orthogonal to either one of these. I know I mentioned this last semester, 169. If you have a vector of 2 components, what's the easy way to get a vector that's orthogonal to it? I don't suppose any of you who were here last semester. That's part of it. You flip the components, that's part of it, and there's one other thing you have to do. You change the sign of one of them, either one. So no change. So we'll take, we'll flip the components and negate one of them. So if this vector works, where both components are positive, or both negative. Well, it's good you remembered half of that. So these are the directions that are orthogonal to the gradient, and therefore the function is not changing at all along those directions. So along this line, that's the direction of the level curve f of xy is equal to 16 or minus 16? Minus 16. Because that is the value of f at this point. All right. So at this point, f is equal to 16, and as x and y change along this line, f remains equal to 16. So that's the direction of the level curve that passes through that point. Whereas if we have some other direction, let's let u be equal to, say, 1 over square root of 2, minus 1 over square root of 2. So that would be this direction right here. Then the directional derivative in this direction of u of your function is going to be fx 1 over square root of 2 minus fy 1 over square root of 2. So we're going to have minus 8 over square root of 2 minus 16 over 2, so minus 24 over v square root of 2. So f is decreasing pretty rapidly as you go in this direction, and that makes sense because this yellow vector here, that's the direction of steepest descent. So it's already plunging at that point. This direction u is right here. It's not too far off from that. So you'd expect it to be decreasing quite a bit there as well, just not as fast. Okay. So for any directional derivative, given a direction, you evaluate the gradient at the point of interest, dot product, and there's your directional derivative. Okay. So questions about this one?
So everything.
So to finish up, talk about, instead of level curves, level surfaces. So here we're dealing with functions of three variables. So solutions of this equation for some function of three variables, f of x, y, z, is a level surface. Okay. Now, so how do we compute the equation of a tangent plane? Now we have a way of doing this already, except it doesn't apply when the function is described in this form. So we have a method for a case where z is explicitly defined as a function of x and y. So we have z minus z naught is equal to partial of z with respect to x at the point x minus x naught plus partial with respect to y at that point y minus y minus y naught. Okay. But that doesn't really help us here where we don't have z defined as a function of x and y. But there is a tangent plane. We ought to be able to compute this equation anyway. So, fortunately,